The last video was shot in a dark room with low power lights shining on the NanoMouse so that I could show the effects of ambient light and how we could filter it out of what our sensors are seeing. If you're programming your NanoMouse in a well-lit room, you're probably seeing results more like this. As you can see, they fluctuate quite a bit. And the question is there anything we can do so that when we see an object in front of us, the values are a little bit more distinguishable. This would allow us to make our nanomouse detect something and then react to it much more easily. Here you can see I've graphed the data that we just collected with the nanomouse, and it does oscillate quite a bit. It fluctuates up and down, and then when I put my hand in front of it over here, you can see the values they continue to fluctuate even though they get higher. The worst part of this is that the lowest values here of when my hand is in front of the mouse are actually lower than the highest values from when there's nothing in front of the mouse. So it's very difficult to distinguish when there's something in front of the mouse right now. It would be nice if this number was higher always than this number. Well, it looks like we can sort of deduce that just by looking at the data, because all of these values sort of seem to, if we were to average them all together, they would probably be somewhere around 10. And these values over here would average to be somewhere around 30. Well, the way we can handle this problem is by finding what's called a moving average. So what I'm going to do is I'm going to take the average of the previous 5 points of data, the current and previous 4 actually, and I'm going to use that. I'm going to try and use that number to base my decisions on. And if we look at this number, when we graph it, we will see that it is indeed, it's quite a bit less variable. There's still a fair amount of variation in there, so I think we could probably improve the number by taking the previous 10 values. Then I'll fill this variable all the way down. And you can see that it's taking the previous 10 the average of the previous 10 values, because this cell is taking the average of these data points, and then down here this cell is taking the average of these data points. So as each one of these goes down, it just keeps taking the average right before it of the previous 10 data points. When I look at the graph, the data has improved quite a bit. We're starting to really converge on a central value, but we're also starting to see the drawbacks of using a moving average. And those are namely that it takes a while before I can even use this information, because I have to collect 10 data points. And then when something changes, when I put my hand in front of the mouse, it takes a little bit of time for this moving average to show that something really is there. So you can see right here, this climb took some time. This isn't going to be a huge issue because our mouse operates in the milliseconds amount of time. In just a matter of milliseconds, all of this happens. So if I put my hand in front of it, it's going to be roughly 50 milliseconds, and then we'll know something is there. It's not a huge issue. But it is something we do need to take into account, and we need to make sure we're not taking a moving average of the 100 previous data points. Otherwise, we will start to run into issues. Before we begin changing the code within our program, we're going to take a little break to discuss exactly how the code we're going to implement works. So off to the left-hand side here, you can see these are the values, some of the very first values we got when we collected some data with our NanoMouse. And we're going to use these to demonstrate what a moving average looks like. So we're going to use what's called an array to store the values that we're going to average. And so if a variable stores a single value, an array stores multiple values. And we're just going to call this our data array. So arrays are referenced by using what are called indices, an index. And the very first time we run through, or we run our sense function, it's going to have we're going to have an index of 0. And so arrays are 0, they start at 0. So this very first item is going to have an index of 0. The next one will have an index of 1. And the next one will have an index of 2. We're only using 3 items here just to make the math a little bit easier and to make the example go a little bit faster. So the first time we run through our sense function, we're going to take our very first reading and plug it into this index 0 slot. And then we're going to have a variable that we're going to add things to and subtract things from. And it's going to be our total. This total is going to keep track of what everything within the data array adds up to. So it's going to be the total of all the items within this array. And so the very first time we run through it, we add what we just put into the array, which is 13. And because it's the very first item, the total is 13. All right? And then we're going to find our average. Our average is just our total divided by the number of items within our array. So here it's going to be 13 divided by 3, which gives us 4.3 repeating. The next time we run our sense function, we're going to put a 17 in this slot because every time we run through it, our index increments. It goes up 1. So here now it's a 1. And so that means we're going to add a 17. We're not subtracting anything because we haven't taken anything out of the array yet. So then our total is going to be 13 plus 17, which is 30. And then 30 divided by 3 gives us 10. The third time we go through this, we're going to put a 14 in the next slot. And that's the index number 2. And then we're going to add 14, which will give us a total of 44. Again, we haven't subtracted anything because we haven't taken anything out of the array yet. And then we just take 44 and divide it by 3. And we get 14.6 repeating. Now, the next step, we actually take this -1 and we put it in place of the 13. So I have to get rid of the 13 and put a -1. And that's because every time I get to the I go 1 0 1 2, I start over again once I get up to 2 because my array is only 3 items long. So here's the first, the second, the third item. I have to start over again. So the 0th item, the 0 index item, gets replaced. And so I'm adding a -1 and I'm subtracting a 13. So I'm actually putting in, this will actually come down to 30 because I'm subtracting 1 and I'm subtracting 13, so I get 30 here, which will make a 30 here. Divide that by 3 and I get 10 again. Then the next item will be the 1 index. 16 is going to go in place of the 17. So I'm going to get rid of the 17. I'm going to put in a 16. So I'm adding a 16. I'm taking away a 17. And so the net result is it's going to go down by 1. This is going to become a 29, which would make this 29 divided by 3. 27 divided by 3 is 9, so this is going to be 9 2/3 or 9.6 repeating. And then we'll go ahead and do one more just to, or maybe two more. Here I'm going to put in a 25 and take out a 14. So I add the 25 right here and subtract the 14. Subtracted the 13 way up here. And so now the net result is I'm going to be adding, looks like 6 plus 5 is 11. So yeah, 11 plus 14 makes 25. So then let's see, this would be 30, 40. So then I get 40 divided by 3. 39 divided by 3 is 13. So 40 divided by 3 is going to be 13.3 repeating. And now we'll do one more just to see the pattern very clearly. Now I have to take this negative 8 and put it way up here in the 0th spot. So I'm going to get rid of the negative 1 and put in negative 8. So I'm adding a negative 8 and I'm subtracting a negative 1. For those of you who know your integers fairly well, this is the same as adding a positive 1. So the net result is going to be subtracting 7, which would make this 33. 33 divided by 3 gives me an 11. So here you can see at the very beginning my value is fairly low, but I do eventually come up with a moving average that is a little bit more stable than the numbers I have over here. Because I'm only averaging the last three values, they still vary quite a bit, but they are a significant improvement over what we started with. To implement smoothing within our code, we're going to have to add a few more variables. I'm going to add them in the private section here because they're not going to be used outside the sensors class. The first variable we're going to need is a total variable, just like we talked about in the explanation previous. And I'm going to call this front total because you're going to want to keep 3 different totals, one for your front sensor, one for your left sensor, and one for your right sensor. I'm not going to go through doing this for your left and right sensors. We're going to focus just on the front sensor to keep the example fairly simple, and you can implement the left and right sensors on your own. The next thing we're going to have to do is create a constant. And if you remember from when we were working with the motors, we have to include this static word before constant here because it's within a class. And then it's going to be a byte, and the name is going to be the number of readings. So how many things are we going to average? And I'm picking the number 20 just because I've done some testing, and 20 seems to work fairly well. Then I'm going to create a variable for our index, and it's going to be a byte because I'm not ever going to average anything that's larger than this number. We declare this as a byte because we're not ever going to average anything that's more than 255 numbers. Nothing more than our most recent 255 readings. The next variable I'm going to create is actually an array, and it's going to be an array of integers, and I'm going to call it front readings. So this is going to store our most recent readings, and I'm going to give it a size, and the size is the number of things that it's going to have in it. The number of readings is going to be equal to, guess what? Number of readings. And because this was set to 20, this array it'll have 20 little memory slots. The next thing is going to be an integer for the smoothed value. So after we do the division, we should get a smoothed value, and we'll store it right here. Once you've created the variables, and we'll go ahead and put a little note here, variables used for smoothing, we have to change our sense function, or we have to add to it. And so after we filter out the ambient light, the next thing we need to do is this is kind of a little bit counterintuitive, but we're going to take the front total and we're going to subtract from it whatever is inside the front, the very first, or the array. And because we're assuming this is the first time we're going through the loop, it's going to be the first item. And the index, because we didn't define the index, it's going to start out with a number of 0. So this is the first time it runs through it. This is a 0. There's nothing in the array right now. So the front total, we're subtracting something from it. And because there's nothing there, we're not really subtracting anything. This little operation may be a little bit confusing for you. Just to remind you how it works, basically what we're saying is this. Front total equals front total minus front readings, the reading associated with this index. A faster way to do this is just to do the minus equals operator. The next thing we're going to do is set the array's value for this index equal to the front reflected value. So whatever we got up here, we're putting that into our array. And then we add that value to our total. And then we increment our index so that the next time we call the sense function, we're messing or we're changing the next item in the array. Now, if the index gets to be larger than the number of readings, right up here we said it was 20. If that gets to be too big, what we need to do, greater than or equal to the number of readings, is reset that index. And we're going to do that by saying index equals 0. And then all we have to do to get our smoothed value is say front smoothed equals front total divided by the number of readings. This basically averages the most recent readings that our NanoMouse has collected. To see this, we're going to have to change our view function so that instead of referring to the single value that our mouse has collected just now, it refers to the smoothed value, which averages the 20 most recent readings. And then to make this happen a little faster, if we go to the main function, we can actually get rid of this delay here, and the smoothing will occur much more quickly. So let's go ahead and upload this to our mouse, and you can see that even in bright light, that value converges fairly quickly. If I go to the very top, it converged. It came to a dependable average in very short order. If I put my hand in front of the mouse, it picks up that change very quickly. And the value that we're seeing is very stable. So this is a number that we can depend on and use to make decisions that will result in consistent behavior. We've squeezed about every last ounce of variability out of these sensors that we can.